Hi, my name is Nicolas. I'm the CTO of the foundation, and today we're going to talk about fees and why we need them and how they help making chains cheap and fair. So why this talk? Well, I wanted to give first a kind of an idea of like why fees need to be so low or so high. Like you can't really actually decide so much. If you think about it, if fees are too low, you actually end up with a unsustainable system that probably ends up using too much of a specific resource for no particular reason. Like think of maybe like people using, I don't know, blockchains to mine some other coins, right? Like it doesn't make any sense. And if it's too high, then you end up with systems that actually nobody's going to use. You're actually hurting your use cases. So what I wanted to do here was to explore what we've been doing at Stellar on that front. Kind of, we experimented over the years on what can be done on the, as incentives on the network. So, starting in 2014, the Stellar network was born. At the time, the model we had was very much what you find in most blockchains, meaning you have transactions that are themselves bidding a fee that you want to pay. And nodes on the network have a transaction queue where they accumulate those transactions. And the game that validators are playing is to decide which of those transactions that are in the transaction queue need to be included in the next block. So what is a block? Well, a block is just a number of transactions that you can include, right? Like you have a maximum capacity, basically. And in the original design that we had, the way transactions were broken down was, and it still is actually, operations. And an operation can be a payment or it could be like a DEX operation. And then the game here, from a block construction point of view, is to solve this classical computer science problem called a NACSAP problem, where the goal is to maximize the total fee that you spend in that block and at the same time fit as many transactions and operations as possible in that block. All right. So like if you look at the slide up here, the transaction queue has like 7 operations inside what is it, like 4 transactions, and if the block capacity is 3 operations, the middle 2 operations or transactions, sorry, are going to be selected, because those 3 end up being the meeting the constraint of 3 operations, and at the same time you end up with a $3.50 in this example total transaction fee. This was came with some problems, and the type of problems we saw over the years was that network conditions actually change fairly rapidly between ledgers. So for example, you have a lot of trading, a lot of payments, and then ledger to ledger, you don't really know if a block is going to be full or not. And as you try to deal with that from a client point of view, as you try to get your transaction included, you need to pay more in fees, right? To bid more, basically, to be included in the next block. And the issue with this is that, like, as you try to come up with a strategy, right, to be included in the next block, depending on your priority as a wallet, you still end up paying actually too much fees. And the reason for that is that it's actually very simple. Like even if you have the perfect strategy, think like you know all the previous ledgers, like their composition, if they are full, and so on, which is actually how most people do it. You look at that and you try to predict what the next ledger is going to be. And the problem is that, well, it's the future, and you can't predict the future. So you end up with often having situations where you're going to either put a fee that's too low, and then if you have a high contention, you will not be included. Or if you, like I said, if you think you have the best strategy, you will end up actually paying too much, and the next ledger is actually not full. So the solution we came up with in 2018 was this CAP 5, which is a variation of this bidding auction system called the Vicre auction that takes advantage of SCP, which is the Stellar Consensus Protocol that the Stellar network is using, and take advantage of the unique properties of SCP in this case. And the unique property I'm talking about here is that validators that are running the network actually do not benefit from transaction fees. So what we could do in that context was reduce the complexity in those clients so that they don't have to predict the future anymore. You just bid as high as you're willing to pay, right? Like for that transaction, and the network will do its best to not have you pay like too much, basically. And to get an idea of what's really going on the example I have here, I have like this transaction queue. For simplicity, they're all one operation each. And I have sorted the transaction queue by bidding size, right? Like the how much they're willing to pay. So like $100 for the most expensive transaction. And then it goes 30, 20, and so on. And with a capacity of 3, what you end up seeing here is that I just need to pick the first 3 transactions. And when we pick the price that those transactions should pay in terms of transaction fee, they will pay for with the cheapest of those 3, so like $20 in this case. And the reason for that is actually fairly simple to understand, is that by paying $20, they will actually pay more than the first transaction that's not included in the ledger, which is transaction 4 in this example, right? And by doing that, we end up actually making the clients much simpler. You don't have to kind of come up with like historical mining of ledger composition and so on. All right. Of course, again, we have more problems. This is something that is maybe not as bad as the first type of problem, but it still exists. So now what we're talking about is that even with this better bidding strategy, right, you still end up with certain traffic patterns that are hurting everybody, like the users on the network. And the type of traffic pattern I'm talking about are trading spikes that are competing with payments. And I already talked about that in a previous presentation, but like the trading spikes I'm talking about are typically arbitrage activity from bots, right, that are trying to take advantage of a specific trade that can be made. Usually it's one trade and in one ledger. And then all other competing trades that try to take the same arbitrage opportunity are going to fail. The thing is that the expected value, so the opportunity cost for those trading bots is fairly high. Like you can make potentially thousands of dollars on a single trade, right? So they're willing to pay much higher fees as a consequence. And when this happens, everything goes up. Like prices for all transactions has to go up if you're just doing what I was describing earlier. So the solution we came up with that actually just went live earlier this year is CAP 42. It gives the capability to validators to break down the transaction set, so the block, into different parts. And again, this takes advantage of some of the Stellar Consensus Protocol properties where validators are actually kind of held accountable between each other, because reputation takes a very strong priority, right? Like when we think about the network health. So in this case, what we could do was let validators partition trading from payments. And it's actually a win-win type of situation here when we give this capability to the validators, because for traders, you actually do not change the expected value of a trade, because you know, like failing 1,000 transactions or failing 100 transactions, you know, with a bucket where inside one of those only will succeed, like the fees that people are going to be willing to pay are yeah, it kind of works out to be the same. And on the other hand, because now payments are not mixed with this type of pattern, you have payments that stay extremely cheap. So we run actually a few experiments this year, and yeah, we could actually prove that this was the case. All right, so of course, new problems, new technology. So we had also Soroban that came to exist earlier this year, launched on the network. Soroban is a smart contract platform on the Stellar network. And in Soroban, you do have a very different type of transactions that came to exist, because now you have to deal with different types of resources. Basically, you have to deal with the number of or the amount of computation that a contract can make, or the type of operations like reading or writing to the ledger. And as a consequence, the knapsack problem I was talking about earlier becomes multidimensional. So like here you can think of like having to fit as many CPU instructions, number of reads, number of writes, as many as possible in one single block, while at the same time you're trying to have fees that are properly computed. So the very first thing we tried to do actually on that front was to just solve that problem as is, right? And the reason you want to solve this problem as a multidimensional resources, right, is it allows you to do very interesting things when it comes to network utilization. So if you look on the board here, I have, to give an example, two transactions, A and B, or two types of transactions, I guess. One, transaction A, uses a little bit of CPU, but does a lot of reading of the ledger. The other transaction is doing a lot of computation, but doesn't read a lot. And if you think about it, actually, I can combine those two transactions in the same block, and will use, in total, a lot of CPU and do a lot of reads, but they don't conflict in a way, right? So I can maximize my my performance on the network by doing that. The problem, of course, that if you try to just compute resource prices, like I was describing earlier, through a bidding system, right, where you try to say, okay, if I have two transactions, and then one bids more for the price of compute, and you know, it kind of changes certain dynamics in a way that is fairly complicated. So that's kind of this bias that I'm about to describe here. And to give an idea of what's happening in this case, is that if you imagine actually the exact same scenario I was describing earlier, where things work great to improve performance, the transaction A here that doesn't use a lot of CPU can actually bid extremely high prices for compute because they don't use a lot of it. So if you are trying to come up with a way to compute the how much to pay for compute, if you end up with this type of transaction establishing the price of compute, then transaction B in this case gets heavily penalized because it's actually trying to use a lot of CPU. So like if you say, well, let's drive up the price by 10x, maybe for transaction A, this impact is going to be single-digit %, right, in terms of total price. But for B, it will be actually 10x. So not so great. Anyway, so we went through a lot of design iterations on this, on trying to figure out how to do fees on Soroban. And we went in a completely different direction at some point. And that's what we actually launched on the network. So this is like described in this CAP 4607, so quite a mouthful. But the idea here is that the resource price discovery, so like deciding basically on how much to pay for compute or for any other resource types really, is not done as part of block construction. So the idea here is that it becomes more of a historical analysis. You compute prices over fairly long periods of time. And then for block construction, you use a different concept that's where this fee bit, the variable part of the fee basically, is really this social value of the transaction. And the intuition there is that how much somebody is willing to pay to get their transaction included in a ledger has actually nothing to do with the amount of resources they're using. And to give an idea of like, why is that true? Well, think about certain transactions that maybe from their mere existence are unlocking a lot of value off network. So like it could be a proof of of being alive or something like that, right? So in that case, the resource utilization is close to zero, but maybe I'm willing to pay thousands of dollars because if I by including this transaction, I get to benefit from it elsewhere. So as we went through those type of iterations, what this allowed us to do was to really get rid of the constraint on the number of dimensions, because now this price discovery doesn't need to happen on a per block basis. And going back to my example earlier of like how much you can basically cram into a block, the more dimensions I have, the more actually I can kind of optimize my block to use as much resources possible on the validators. And using just ledger read access as an example, we actually broken it up into two parts, IOPS and number of bytes. And the reason why we did that is, well, the hard drives, at the low level, they actually have two resource types like that. And if you're thinking ahead, like where we will be in a few years, like one of those limits will actually be extremely important. And then same thing on transaction size. We have network bandwidth that is used only really once. Like when you submit a transaction, you need to propagate this transaction across all the network, right? That's going to use network bandwidth. That should probably be priced differently than the cost of storing this transaction in those full validators, right? The archives in that context. And the reason that they should be priced differently is that those full archives, they will actually be accessed forever after, right? As people try to audit the activity on the network. All right, so now that I talk about what happens on layer one, you can actually think about the problems I was describing as existing actually at all layers and in other forms. It's not necessarily just about resources. So like using actually another example that we have on the network that's not a clean resource type like that. We have the notion of ledger state rent that we're working on as we speak, where the fees there are really to help create the proper dynamics in terms of which part of the ledger should be accessible at any given time. Then if you think about dApps themselves, still activity on chain, you have classical ways for those dApps to kind of make financial sense, where they have like trading fees. That way you can attract, in the case of AMMs, for example, liquidity providers, and in exchange, they will get some fees. And then off-chain, it keeps going, right? Like you have infrastructure providers, so like RPC nodes, indexers, all those things. They need to. I mean, they are not doing that from the goodness of their heart. They need to make money. You want to have the right incentives. So really, when you think about the implications of fees, you have to think at all levels of the stack. So, what did we learn today? I think that the main thing I want people to kind of remember is that fees are actually a good thing. You need them so that you have some anti-spam measures, you have the right incentives, and at the same time, I think that with the right desire, right, from a tech point of view, we can actually solve the equitability aspect. I think there is hope that we can get both, basically equitable use cases, fair fees, and scalability. But yeah, this requires quite strong opinions, I would say, and for that, you can't just leave it for anybody to solve it, right? I guess that's it for now. Thank you. Thank you for listening. If you have any question, please find us on our Discord. Those are conversations that are constantly happening, and where you will find probably help if you need it.